Today we have the last episode on this series, which is all about GaN-on-SOI technology for highly integrated GaN ICs. And to speak about this topic, we have two wonderful speakers. First of all, we have Dr. Urmimala Chatterjee, who received her bachelor degree from WBUT in India and her master's degree from the Technical University of Munich in Germany. After that, she pursued a PhD in SAT-KU Leuven on power converter design for PV applications. And right after her graduation, she joined TSA Belgium and worked on discrete circuit design for space electronics applications. Currently, she is a researcher working at imec in the GaN for power electronics applications department, and her main responsibilities deal with the GaN IC activities and device designs. Then we have a second speaker today whose name is Maritza Tangarife Ortiz. Maritza received her diploma degree in physics engineering from the National University of Colombia and her master's degree in photonics from the University of Jena in Germany. After that, she worked as a researcher in different institutions from Colombia and Germany as well, and in many different topics ranging from optical design, holography, or laser integration. At imec, she joined first the imec Silicon Photonics multi-project wafer service and worked in different tasks of this service. And just 3 years ago, she stepped up and started the GaN IC multi-project wafer service business, which she's currently coordinating. So having said all of this, I would like to invite to the floor our speakers, and I wish you all a very nice webinar. So Urmimala, Maritza, the floor is yours.
Thank you, Maria, for such a nice introduction.
Thank you, Maria. Yes.
You're welcome.
So, hello everyone. I'm Urmimala Chatterjee. Today, I will talk on GaN-on-SOI technology for highly integrated GaN ICs. Okay, so we all know it's now a fact that gallium nitride HEMT switches starts to play a crucial role in power electronics industry. That we can see from this graph as well, that gallium nitride started from the consumer electronics, and now the applications of these switches are growing, and it is also part of now the high power electronics industries, for example, in the automobile, aerospace, or power supply units. Also, you can see that how the market share is growing of these GaN switches, and that shows that this is gaining popularity day by day. Now, why these GaN switches are becoming so popular? Because it has some inherent quality. As it's a HEMT device, high electron mobility device, it can offer high switching speed. It means it leads to high frequency operation of the circuit. Also, if you see in this graph, it's a graph with on resistance versus breakdown voltage, you can see that gallium nitride has lower on resistance at higher breakdown voltage compared to its silicon counterparts. And that also leads to high efficient circuit design at high power. However, till today, gallium nitride switches dominate the market by off-the-shelf discrete components. Now, this extremely good frequency capability introduces some challenges to operate the transistor efficiently. We all might know that it has like gate ringing, and it's quite some issue at the false turn on. Why? Let's say that we have a discrete HEMT and that needs to be driven by a gate driver. So no matter how close we place the gate driver with the switch in a PCB, we see that there is a parasitic inductance and parasitic resistance in between. Now these parasitics together with the gate capacitance forms a LRC charging path, and that creates a ringing and oscillation during the turn on and turn off. That definitely also at the gate side and also reflected at the output side. So it means it impacts the switching performance, and sometimes it's so high that it impacts the gate reliability. And when what happens during turn off? Due to the high dividity and very low gate capacitance. Now, because of this low gate capacitance, it makes a high switching frequency device. However, because of this, when it turning off, it discharges so fast that it creates a voltage peak during the gate. Now, at the gate, this voltage peak, it's sometimes significantly higher that it crosses the threshold voltage of the switch. So it means when it is turning off, we see for a very small time, the switch is turned on again. So it means during turning off, we see a false turn on phenomena, which is not wanted. So to reduce that, one of the quickest solution we can think that we can place the gate driver as close as possible to the switch so that we can reduce the loop parasitics as much as possible. Or we can actually integrate it, this driver together with the switch. So this monolithic integration can eliminate this loop inductance completely so that we can avoid such ringing and such kind of disturbances. So therefore, monolithic integration can highly reduce or completely eliminate this gate loop inductance. So therefore, this is one of the reasons that we need GaN IC to efficiently use these switches. Besides that, as you see that GaN IC provides even higher switching frequency capability compared to its discrete GaN hemp and other silicon competitors. So it means that it gives a possibility to integrate higher power. So therefore, that it can have leads to a high frequency operation, which at the end helps to build a smaller, lighter, faster, and cheaper device. Because we know that as high frequency we goes, the passive component sizes are also reduced, the cost is reduced, and that can help more efficient, cheaper, and smaller, more compact circuit. Also, because it helps to reduce the gate overshoot, undershoot, as I explained in my previous slide. So it also gives a more robust operation. Therefore, I'm convinced to fully utilize this fast switching GaN technology, monolithic integration is very essential. So in today's talk, I will talk about these GaN IC solutions. So what are the challenges we face when we started doing this monolithic integration and how we solve it? And in the second part, I will show you some GaN IC demonstrators made by our imec GaN IC technology. And then the last part, we will cover that how you can use this GaN IC for your own design through Europractice. Let's start with GaN IC solutions. So what I mean by discrete components to GaN IC, let's say I want to have a half-bridge switch. So half-bridge switch means two switches are connected in series and that forms a half-bridge switch. Now we can have everything in discrete. So two discrete power switches together with a discrete driver that is driving these two power switches. So it means a complete discrete solutions in 3 die. Now we can go one step ahead and we can integrate those in 2 die. How? One switch and its integrated driver in a single IC. And two such ICs we connect in series to have a half-bridge switch and its driver. So it's a 2 die solution. Or we can integrate both such switches in a same IC and that can be driven by an external driver. So it's also 2 die solution. We can go one step further where we can have all of this driver and the two switches, everything together in a single die. So that's what I mean, starting from the discrete to a complete integrated solutions. And we now have this from 3 die solutions to a 1 die solution where the both switches and driver is integrated in a same die together with other functionalities of the driver. And everything is in all GaN technology. Now, definitely we have faced some challenges while we are doing this monolithic integration. I have divided in between technological and circuit design problems. In case of technological problems, we see the backgating effects when we try to integrate a half bridge, and low voltage control and diagnostic circuits is also needed. Suitable passive components needs to be designed to have a logic or analog circuits in GaN IC technology. The another part is definitely the circuit design problems, because in gallium nitride, we do not have a complementary device. So if I compare with the CMOS, we have kind of only NMOS, you can think like that. So because we do not have a complementary device, it creates another level of complexity, designing a driver circuit and designing an analog circuit. Now, technological problem. So let's start with a known effect we know in CMOS, that is body effect. Now, what is a body effect? So when we see that the source and bulk potential are not zero. So if there is a difference in between the source and the bulk potential, if in a NMOS, let's say, then we see that it influences the threshold voltage. And that you can see in the equation actually how it has a positive impact and it changes the threshold voltage. Now the threshold voltage is generally must be influenced by the gate only, but we also see that there's another influence there. So we call it a backgating effect. So there, you see this is a picture of an NMOS in P-well, and when this source and bulk potential are not same, then we see the backgating effect. And we also see the similar effect in P-GaN. Now here, again, I have shown you the picture of the NMOS in P-well, and this is a cross section of E-mode hemp with a P-GaN. And this is made on silicon substrate. Here I show you source with source metal and the fill plate, gate with gate metal. Now, when the source and the bulk potential are not same, we see an exact similar backgating effect as you see in NMOS. So why it is very prominent in case of half bridge? Let's say we are again talking about a half bridge which is a complete discrete solution here. So here you can see that high side switch and low side switch, both switch are, because they're discrete, so it has own substrate, and the substrate and the source can be connected together. So there is no backgating effect because source and substrate potential are zero. So the difference between source and substrate potential is zero. And now we want to have a monolithically integrated half bridge switches. What will happen? We have a single substrate, it means. So the substrate, we can either put it on zero potential or in high voltage potential. But we know that here this source of the high side switches are floating. So it means this particular node can see the zero ground potential, also very high potential as high as VDD. So we will, whatever we do, we will see that the source, both of the source cannot see the same potential, and there is a difficulty to have a single substrate. Now to elaborate this, let's say I have a half bridge switches, which is V in is 200 volt. Now when the high side switch is on and the low side switch is off, so that time the P, this point we'll see, yeah, lower than the RDS on, so it's kind of 199 volt. When the low side switch is on and high side switch is off, then this potential will see 0 volt. So for example, if I connect the substrate to 0 potential, so it means the source of the low side switch is 0 potential, the substrate of the low side switch is also 0 potential, so there is no backgating effect in low side switch. However, because it is in the 0 potential, when the high side switch is on, we will see that there will be a huge voltage difference between the source of the high side switch and the substrate. And definitely we'll see the current in substrate. And if we decide that we'll disconnect the substrate completely and we will keep it as floating, so there also we will see that's a significant backgating effect as the substrate is not connected to the again source of the high side switch. Now, to solve this problem, we propose to build the high side switch half-bridge switches on SOI substrate, silicon on insulator. So here you will see that we have one thin silicon layer, and also that's 111, and then a thicker silicon substrate, and in between that we have a boron oxide. Now with this and the oxide filled deep trench, we can isolate the high side and low side switch from each other and from the silicon substrate. So here you can see that the thin silicon layer can be connected with the source of the high side switch and the source of the low side switch individually, and with these strange isolations they can be completely isolated. So now there is no problem that if the source of the both switches are different and therefore their own silicon 111 substrate. And that's how we can completely isolate both of the switches, and still the source and substrate potential for both of the switches are 0. So that will help to eliminate the backgating effect. Now here in the electrical measurement, I will show you here in picture A. This is on a silicon substrate. And picture B, this is on SOI substrate. In the silicon substrate, you can see that there is no possible to isolate this, and therefore when we measure it, we see that at higher voltage, the normalized current is reduced in case of silicon. So you can see the significant backgating effect. However, the ID current, the drain current is almost constant in case of SOI solution, and even up to 200 volt, up to very high voltage, we see that the normalized current is not reduced. So it means that by doing this, it's possible to completely eliminate the backgating effect. Now, you can say that I want to keep the silicon 111 substrate floating. And then what will happen? We have also tested that, and we have seen that even if the substrate is kept as floating, it is not connected to any potential, still we see a significant backgating effect in case of silicon. The reason is that it takes a voltage and an unknown voltage, and then again it shows the backgating effect, and drain current it's reducing. So if we need to integrate everything in all GaN, then we also need some low voltage components to realize an analog circuits, or let's say to design a driver. We have low voltage components and we have logic P-GaN HEMT. So in our technology, the logic P-GaN HEMT has a similar structure of power HEMT, but with shorter gate width. And we have tested up to 2 micrometer gate width that you can see here. And you can also see that even with the lower gate width, the threshold voltage is unaffected. And definitely because it's a logic HEMT, so we have like up to 20 volt logic HEMT, that the gate to drain distance is shorter. Also, you see that the IG and from the ID current, the leakage and things are very low. Besides that, we need some passive components that is also used in the analog circuit design. So we have high ohmic resistor that we realize through a 2-day gas. And that is, we have 600 ohm per square. Also, we have low ohmic resistor that we make through ohm metal, and that is like 1.7 ohm per square. And we also have some small beam capacitor to be integrated, that is 0.3 femtofarad per square meter square. And here I have shown you the cross sections of these passive components. Now we have 200 volt GaN IC and 650 volt GaN IC and 100 volt GaN IC. For 200 volt and 650 volt GaN ICs, that is PDK released for all three options, and for this 200 volt and 650 volt that is available for MPW. So through the MPW service, you can access our technology. And for 100 volt, it is not available yet for MPW, but it is available for dedicated run. Now, the second part, that is a GaN IC demonstrators. And I start with the circuit level challenges. Now, as I said that in gallium nitride technology, do not have a complementary device. So it means we cannot realize a TTL logic while designing a circuit like transistor logic, what we are used to for CMOS design. So then to do that, to realize this kind of circuit design in GaN IC technology, we need to go for RTL design, register transistor logic. And therefore, by increasing the resistance value, we can definitely increase the gain, but that comes with the penalty of switching speed or the delay in the circuit. So therefore, that through this RTL design, there is a trade-off between the switching speed, power dissipations, and the gain of the circuit. That is the biggest challenge to design a driver circuit, any kind of logic gates, or the analog sub-circuit for using an RTL design. So here is some logic gates we have realized through our GaN IC technology. As I said that we need to go for RTL design. So you can see the inverter is realized with the E-mode hem together with a resistance in series. This we realize with a 2-deck resistor. And this is after fabrications, the inverter and some type of NOR NAND gate and the flip-flop. And through everything through the, so this is a building block, this kind of inverter circuits for GaN IC design. And through this, we are able to realize different type of logic gates. From the measurement result, you can see that it's working perfectly. So we have here a one comparator circuit. Again, with the RTL logic, we have the comparator circuits, and from the measurement result, you can see that here a reference voltage of 4.5 volt is set. So when it is crosses the reference voltage, then when the VDD crosses the reference voltage, then the output toggles. That is basically a comparator functionality. And also a VLO circuit under voltage lockout circuit. This kind of circuit we use in a driver quite often as a protection circuit. And you see that from the measurements, so this is a circuit schematic and this is a processed UVLO circuit. After processing, when you do the measurement, we can see that it perfectly works. So it means when the voltage here, the VACS is follows the voltage of this one, and the reference voltage is 4 volt use. And when we see that the voltage is lower than the 5 volt and it goes to the lower than reference voltage, then the UVLO triggers a high output, and then it will give a signal to shut down further the driver. So we have some under voltage lockout circuit, different type of protection over temperature protection, over current protection circuit, and that everything realized all GaN IC technology. Here I want to show you a demonstrator building blocks. So we do a different type of basic building blocks in GaN IC technology to have like proof of concepts, where you see here it is a 200 volt half bridge switch with integrated driver. And here is a measurement result. This is like at 1 megahertz switching frequency. We have tested this. The driver, it's just a basic totem pole driver, and it has an integrated level shifter. And you see that the switching transition is quite fast and it's a very smooth signal. So that kind of yeah, I have only shown here one IC1 driver, but that kind of driver, analog circuit, protection circuits, that everything can be integrated through this technology, and we can realize an half bridge switch or a low side hem, let's say, with its integrated driver. Now, there's a third part of the presentation, how you can access this technology through Europractice. I will hand over this to Maritza. She will take care from here.
Okay, thank you very much, Urmimala. Thank you, Maria. Good afternoon, everyone. So here I would like to talk about what is imec's GaN IC offer via Europractice. So it's okay. Can continue. So first I would like to tell you that there are currently two public PDKs offered via Europractice. These are the 200 volts and the 650 volt PDK, as well as Urmimala has already explained. Using the trench isolation, well, you can integrate multiple transistors on the single IC. She has explained how you can reduce the system parasitic inductance. And I would like to include that you can also save a lot of package costs with it. So imec's GaN IC technology is available via the MPW services. For those who are not familiar with the MPWs, the MPW stands for multi-project wafer. So here, several customers share the cost of a lot, of fabricating a lot, and every customer pays proportional to the area that they are using. Yeah, so this is a very good option for those researchers and startups who want to prototype some designs. So yeah, next please. Our PDKs currently contain process documentation, layout guidelines, verification, and models. And library devices, we have now low and high ohmic resistors, metal MIM capacitors, low voltage logic devices. And well, in the roadmap, there are other components waiting, but it takes a while to bring them into the MPW. Though with these components, well, we have we have already several examples of highly integrated GaN power systems on a chip. So yeah, there are really several possibilities with it. And well, the good news is that the access to this PDKs is free. Basically, anyone who belongs to an institution, recognized institution, can access to them. And the way to do it is just signing the design kit license agreement. You can contact us a bit later via our email, and we can give you all the information now about how to get access to it. Yep, Urmimala. Well, I would like to go briefly through the next 4 slides. This is basically all the, here you have basically all the key electrical parameters for the PDKs. You will have it for the 200 volts and 650 volts. And in general, what you can see are the absolute maximum ratings in there, dynamic characteristics, as well as, next please, Urmimala, sorry. As well as typical IDs and VDs curves. Also, all the temperature dependencies. Here you have some interesting graphs for 200 volts. Maybe we can go to the 650. Yeah, next. Yeah, thank you. So yes, again, on-off state characteristic, dynamic characteristics. I understand well as researchers and engineers, we and you are very interested in all the details of these numbers. Feel free to go through them. You can always ask this technical questions about it. This is public information, so don't hesitate contacting us about them. Next, please. Yeah, here again, we have the typical IDS VS curves and temperature dependence for the 650 volts. Yeah, next, please. With the idea of widening the types of applications and mostly the logic applications of this technology, we are offering now the copper RDL and copper pillars. I also understand there are different types of packages. We don't push for any specific type of package, but now most of the customers are going for the RDL and copper pillars option. And for some other experiments, people go for the wire bond option. The wire bonding is not something we do regularly, but depending on the number of designs that we receive with these conditions, then we go with it. We split the lot. but I think it's important for you to know that basically the standard for now is the RDL with copper pillars and this PDK. Yeah, maybe next. Well, yeah, we have successfully applied this on 4 MPW GaN IC runs. We do the wafer thinning. We do the dicing and pick and place. They also, I would like to mention, backside metallization is possible, but is not yet offered. It depends on what majority of customers need. Yeah. So even if the technology is developing at a very high level, we need to adapt somehow to the needs of the market. Yeah. Please. And here I like this graph a lot. This because 3 years ago when we started, we presented the PDKs and the technology to different institutions and companies, and though they were surprised with the high level of sophistication of this technology, they were hesitant about whether taping out or not, or prototyping or not. They were asking, this is too good to be true, but who is doing it? We want to know. We're very happy to see that in 3 years, well, we have, after now 5, we're going to our 6th run. Well, we have grown tremendously, and we have customers, yeah, all over the globe. And yeah, that's what we want you guys to know. There are very big companies involved, and there are a lot of institutions taping out now using GaN. So this is basically an invitation. Well, also it's important to know industry is around 30% of our, they are 30% of our customers, and around 70% of them are from academia. So just for you to see, I think we will see that the orange share here in the circle is going to be growing. It is growing actually. Yeah. So this is for you to know that there are many other that started working with this technology. Yes, Urmimala, please. And we're also very happy to share this information. Well, this was new at the end of the last year, but last year we launched a contest for new users of the GaN IC technology. We had 3 winners. In the first place, we had the Aachen University. Well, they brought a fully integrated GaN converter, well, a circuit based on high voltage half bridge output stage with integrated drivers and a lever shifter. Second place, we had KU Leuven. They presented an all-GaN direct AC-DC power converter IC. And in third place, we had the University Leibniz Universität Hannover. And well, with their design, they enhance the efficiency of in offline converters for home applications. And we are very happy to present this because we had more than 10 applicants for this contest, and it was quite difficult to choose the 3 winners. So it means that the range of possibilities is still very, very wide. So we would like to invite you to be part of this. And yeah, they are part of our GaN MPW5 now. So this lot is processing. So yeah, by June, July, we shall have news of the results. Yes, please, next one, please. Well, and finally, I would like to tell you that this year we're going to have 2 runs. Now in May 18, we will have the 200 volts run, and by October, we will have 650 volts run. It is important to mention that the registration deadlines are closing 1 month before the official GDS submission deadline. Also, I have here that the return time is around 24 weeks, but for processing and dicing, consider this. And we have 6 additional weeks where we run DRCs on your designs. So we make sure that they fulfill all the requirements to go into production. Yeah. As I said before, this service is offered via the Europractice platform. As today, I'm not aware of any other, let's say, GaN technology being offered via Europractice. You can always check. Yeah, and prices are starting 17,000 euros this year. Yeah, they are subject to change. This is just informative. And there are small blocks let's say, available for academia. So yeah, you're very welcome to participate and send us all your questions, either technical or just in the logistic part of the MPW. So next one, please. Well, thank you very much to Dr. Urmimala and to Maria for the introduction and the explanation, and also I would like to thank to Europractice project. Yeah, that is helping so many technologies to reach the public. Well, also, if you want to contact us, here's our email. And yeah, we're eager to take your questions. Thank you very much.